All right. Good morning. Let's go ahead and get started. We've spent the last couple of weeks thinking about sorting. And the big benefit, the big win that we get from sorting is first and foremost the opportunity to do a quick search on our collection for whichever data we happen to need. So we've gone over the fact that if we have a sorted array, we can do a binary search, which is going to be log n time to locate an item. We've also discussed the fact that log n time is pretty fast. If the time to search grows logarithmically with the size of the list, we found by doing some calculations that we could have a list with, say, 500 million elements and find something in, say, 30 comparisons. So this is a huge benefit. And the trouble with this overall approach comes into play if we need to continuously edit our list. So where this is a good solution is if the sorting is a one-time event and then the subsequent searches are frequent. So in other words, you've got a big collection of stuff. You sort it once, and then you can search it whenever you need to search it. If that's what you're doing, this is a great approach for finding information. But this isn't always what we're doing. Specifically, it's pretty common to have ongoing inputs of data into a collection as some kind of a program runs. Again, this isn't always the case. In fact, what first motivated this approach was creating a dictionary to back up a language translation program. So that's a great example of the sorted static array. Dictionaries don't change that much. But a lot of situations do involve ongoing change with data. And this is exemplified in particular by applications involving the use of a graphical user interface, right? Where you're constantly entering in new data, and you might in turn have to be able to access it fairly quickly. So for these incremental situations, this combination of data structure and algorithm isn't really enough. We need to have some kind of a means of maintaining data in a sorted, ordered way that allows for a binary search type lookup, but doesn't require us to sort the whole thing over and over again. And we're going to, over the next several weeks, examine several distinct ways to do this, as a matter of fact. What we're going to look at today is a really interesting way to do this, which is called a skip list. So to understand a skip list, we're actually going to begin by reviewing just a regular singly linked list. And what I would really want to call to mind here would be your memory of, in our bonus exam about linked lists, we had this question about inserting an item in order into the list. Doing that is at the heart of the idea of the skip list. So the skip list at its root is really just a singly linked list maintained in sorted order, but with some help. First, we're going to talk through maintaining a singly linked list in sorted order, and then we're going to examine the idea of the help or the augmentation that lets us skip around it efficiently. So let's just imagine a small collection of data that we want to insert into a linked list, keeping it in sorted order. So we'll use some of the numbers that we've been using in some of our examples. Something like this. So let's imagine that I'm inserting these one at a time into a linked list. To simplify the implementation, the approach that I'm going to take here is I'm going to begin my list with a dummy node. So in other words, when I create it, there is always this initial node that contains no value in it. Alternatively speaking, you can imagine that this is a node whose value is always less than any value that would ever be inserted. Okay. So it's like an arbitrarily small value. So now I'm going to insert a 5. So initially, it's pointing to null. So I go in, I find that this non-value is, of course, less than 5. And the value after it is null. So what I'm going to do is I'm going to create a new node containing the value 5. And the thing after 5 will, of course, be null. So now I want to insert a 2. Well, I begin examining my list. A 2, of course, is greater than this non-value. But it's less than 5. So what I have to do is I create a node for my 2. It's going to point at that next node. And then, and this is all very familiar, right? We've done this quite a bit. I'm going to erase that link. And now that is going to point at my 2. So now I'm going to insert a 7. And this is less than 7, this is less than 7, this is less than 7. I get to the end. So I am going to create my 7 node, and it, in turn, will be pointing to null. So now I'm going to insert 3. That's less than 3, that's less than 3, but that's greater than 3. So, again, note the order of events, right? I first create a node containing the value 3. I assign it to point at the thing that's bigger than it. And then I change its predecessor's next link to point at it. And now I've got 4. So 2 is less than 4, 3 is less than 4, but 5 isn't. So I am going to come over here. My 4 is going to point at 5. My 3 is going, whoops, really now. My 3 is going to point at my 4. So now I'm going to insert 6, less than 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 6, greater than 6. So I will create a node for 6. It's going to point there. Then I'm going to erase this link here, and it's going to point there. Yes?
Well, okay, so this next one's going to confuse. What in the case of like where a number is equal to another number?
You know, that was not intentionally part of my example. I think what I really wanted there, whoops, come back. What I really wanted there was a 1. Now, that said, it's a great question, Morgan. And the answer is, what kind of a collection do you want? Like, there's no uniform answer to that. There are 2 ways of thinking about it. The first way is to ask, is what I have a set in mathematical terms? If what I have is a set in mathematical terms, then it does not admit duplicates. And if it does not admit duplicates, if I try to insert the same value, then I'm going to ignore it once I encounter that the value is already present. Or I might have instead what is called a bag or a multiset. That is, I do allow duplicates. And then I would put it right next to its twin, and the order doesn't matter at that point. So that's how we can think about that. But yeah, I was attempting to finesse that issue by not having duplicates and inadvertently failed. Anyway, we're going to talk about that issue though a little later in the course. All right, so now we're going to insert the node 1, and I'm going to allocate it over here, and then I'm going to change the link from my dummy node to point to 1. And because 1, of course, was less than 2. And then at the end, I get 8, which, of course, everything is less than 8. And so it winds up out here pointing to null. Now, this whole time, I have maintained it in a sorted ordering. By itself, with a linked list, that may seem pretty useless. And the reason it may seem pretty useless is that binary search is not a meaningful operation on a linked list. The reason being, this is not an array. I don't have constant time lookup of values. I can't do binary search. But it's worth thinking about what I can do. What is it that's actually a possibility with a linked list? And what I can do is I can hang on to a reference. So for instance, I might at some point have had cause to search my list. And at that time, I might then decide to keep that reference hanging around. Like at some point, I really, really, really needed to know what was at the number 5. And so I could have some kind of external, wow, that was messy handwriting even for me. Let's try that again. I could have some kind of external reference to that node. Now, having that external reference, I can ask that external reference a question, like, what's the next biggest thing? And it can come back, and in constant time, it can tell me that that next biggest thing is a 6. So again, so far, we're not in a situation where we've improved tremendously on an array. If I've got an array with indexes, I can do the same thing. The point more is to show that this structure, as long as we've got some notion of external links, really does have some added informational value as a consequence of being sorted, right? So that's what I can do with one external link. So the really fascinating part comes into play where here's really the key crucial idea of a skip list. I could have multiple external links that are kind of scattered randomly through it. So think about what that might imply. Let's say I've got a skip list with 64 items, okay? And now let's say I randomly have assigned 8 of these external links. So they're just sort of randomly scattered through the list. They're roughly equidistant. At this point, I might be able to say, scan these 8 external links. And, you know, just to really bring this home, what we're doing, we might keep these 8 in their own sorted list. See, if we do that, then what we could do is scan the list of these external links until I find that I'm in roughly the correct territory. Then I can dive into my sorted linked list and know that I'm roughly 8 hops away from finding my item. Of course, as you've already been experiencing, if we can put in one level of abstraction into a data structure to simplify it or improve its efficiency, then the bigger things get, at some point, as computer scientists, we will feel this inclination to throw in another level of abstraction, because that's what we do, right? So maybe what I would have is some higher level list with two external nodes that point into that list. And so I wind up having this hierarchy of sorted linked lists. So let me write that down. A skip list is a hierarchy of sorted linked lists. So in this hierarchy then, at each level, we have this bottom level, and that bottom level has everything. At each level above, we have randomly picked some nodes from the level below to be represented at that level up. So we're going to build our list again using these same numbers, but we're going to think about it in terms of this idea of a skip list. And we'll see how it looks. So, you know what, I'm going to just go ahead and erase this mess, and then we'll put our skip list in place. Something like that. Okay. Like before, we're going to begin with a dummy node, and that dummy node, its value is always less than any value we might insert. So I'm going to park my dummy node back here. All right, so now I insert the number 5. And so I create a node for the number 5. Now, it has a pointer to null, and the dummy node has a pointer to it. But now we're going to introduce the skip list idea to think about how this scheme is going to work. And the idea is essentially as follows. Every time we create a node, we have to decide how many levels of the hierarchy is it going to belong to. And that decision is made randomly. So I am, in effect, going to flip a coin. And if it comes up heads, I'm going to add a level to the node. And so as it happens, this coin flip came up heads by pure chance, not by my design, pure chance. And so there is this additional pointer to null. And you know what? By pure chance, I think it's going to go to one more level. And that will point to null. Now my dummy node needs to have as many levels as the node in the skip list with the largest level. So my dummy node is going to become a little linked list snowman over here like that. Now, for some given height, if we've got a 50-50 shot of adding a level, it's worth thinking about what's the probability of reaching that given height. So for instance, a height of 1 is going to have a probability of 1. We're always going to be the node will always have at least one link. For a height of 2, the probability will be 0.5. For a height of 3, it'll be 0.25.
Wait, for every, so it's, okay, so Is it one? So the case in the probability case, it's 1 divided by 2n or 2
2 to the height, yeah.
to the
Yeah.
n. That's like,
Yeah. And so with a height of 4, the probability is 125. With a height of 5, it will be 0.0625 and so forth,
watch speed.
right? In other words, it gets cut in half every time. So now we can think about the converse of this, which is for a given number of nodes, how many nodes do you expect at the given level? And in effect, what we're saying is, if at the base we have n nodes, the next level will be n over 2 expected. The level above will be n over 4, and so forth. Okay, so let's start inserting some more nodes. You know what, in retrospect, I really should have moved this over here because we've got a lot of nodes to insert. So if you'll be patient with me, let me go ahead and make that move, and then we'll start inserting some nodes. So all this is going to be erased for the sake of what we will soon be doing. And these links are going to extend out all the way like this. And then we got null, null, and null. Okay. So now we're going to look for the number 2. And when we look for the number 2, we're going to start by checking the top list. And we're going to see where in the top list is some node that is greater than 2. So the dummy is never greater. But we look one node ahead, and it turns out this node right here is greater than 2. And so now it's time to insert a 2 into our list. We start with the insertion at the bottom layer of the list. And we find 2 is in fact less than 5. And so we're going to insert a node for 2 right there. So the dummy is pointing there. And 2 is going to flip its coin. It's going to get lucky. And it's also going to exist at that level. But then it's going to get unlucky, and it's going to stop right there. So the coin flip didn't work out. All right. So now we are going to insert 7. And we go to the top level. 5 is less than 7. So we keep going, and we hit null. Now notice something really interesting. 2 didn't make it to the top level. So we didn't check against 2 when we were inserting 7. We skipped 2. So 7 begins by being inserted at the bottom level. I'm going to make this, whoops. I'm going to extend this out a little bit. So 7 will go here. Then we've got a pointer to null. 7 is going to be criminally unlucky and only exist at the bottom level. All right, so now we're going to insert a 3. So we go through our list. At the top level, we find that 3 is less than 5. So now we have to go down a level to see where to put 3. And when we go down a level, so 3 is less than 5, so when we go down a level, we have to go down a level in the node that we're at. So here we look ahead. 3 is less than 5. That's not going to work. We go down a level here. And now we go forward. 3 is greater than 2. 3 is less than 5. Now we go down a level here. 3 is greater than 2, less than 5. We try to go down a level. We can't. We're at bottom. So it's time to insert 3 into the list. And so our insertion, as always, means we allocate that node. We have it point at its successor, and we change its predecessor to point at it. And 3 is going to get unlucky and not have any nodes at the higher levels. So now we're going to insert a 4. So when we go to the top level, 4 is less than 5. We have to go down a level. 4 is greater than 2, but less than 5. We go down a level here. Now, 4 is greater than 2. It's greater than 3. It's less than 5. We run out of space. Whoops. So we are going to insert 4 right there. And 4 is also going to be unlucky.
Wait, so the first few levels are dependent on the first 2 levels are dependent on the second number? Whatever goes in the first 2 levels is dependent on the second number in the list number of list of numbers you were given. So like 5 to 7, 3. Well, like so 2 in this case. So in this case, wouldn't 1 just be the only case where there would be a number on the top level?
Whether the numbers on the top level is chance. It's randomly determined.
Okay, I have no idea. This is confusing. This is already confusing as it is, but whatever.
And you also missed several minutes of the lecture.
Sorry. Yeah.
Okay. So backing up, now we're going to insert 6. We come up to the top level, and unlike the last several insertions, 6 is greater than 5. Now after that is null, so we go down a level. After that is null, so we go down a level. We're at 5. We check ahead, 7. We get to insert 6 here. Now, when we perform this insertion, I think it's really valuable to notice how many comparisons we skipped by virtue of having that top level. To insert 6 into the correct spot, we were able to skip 2, 3, and 4 entirely. We ignored them completely. 6 is going to be a little luckier, and it's going to exist at level 2 as well. All right, now we're going to insert 1. So 1 is less than 5, so we have to go down a level. 1 is less than 2, so we have to go down a level. 1 is still less than 2, and now we're at bottom. Whoops. So we're going to insert 1 right here. And now we get to 8. 8 is greater than 5, but it's less than null, so we go down a level. 8 is greater than 6, but less than null, so we go down a level. And then we find it's greater than these guys. And now we're able to insert it at the end, like so. And it'll be unlucky, and that's the only place it's present. So that is a skip list. The idea of the skip list is that each node is a member of one or more sorted linked lists. By virtue of its membership, you search starting at the top levels and then jump ahead according accordingly when you're doing the searching. Any questions so far about the skip list?
I'm a bit confused on the randomness of the first two of my leveling, but that's just something that I'm gonna have to get more explanation from.
So the part of the lecture that you missed was that what we're creating is a hierarchy of sorted lists. Each element in each list in that hierarchy has smaller and smaller numbers of members. By searching higher in the hierarchy, you get to skip over nodes that are not in the members of the lower levels. To ensure that the higher levels have fewer nodes than the lower levels, whenever a node is added, we randomly determine how many levels it is a member of. So on average, the bottom level, of course, will have a node for everything added. The next level has a node for half the things, the level above for a quarter of the things, and so forth. So that for an arbitrary number of levels, we have a relatively small number of items at the top level.
Okay, then explain to me how there's only three numbers in the second level and none in the first.
There's an element in the first.
Well, my bad. I'm sorry. I forgot the 5. Forgot the 5 exists there as well.
Yeah. So it has 2, 5, and 6.
Yeah.
They were just randomly chosen.
Okay.
Yep.
Okay. That was just something that confused me.
Mm-hmm. So this may look cool, but what we really need to do is think carefully about how many comparisons we need to perform to find a spot in the list given this scheme. And the way that we're going to determine this is to make some assumptions about the number of elements to be searched at each of these various levels. And those assumptions are grounded in the idea that in the case of an isolated node or a list with a very small number of items, these proportions might be wildly different than this. But in a sufficiently large list, we can state with a high degree of confidence that level 2 has half the nodes of level 1, level 3 has half the nodes of level 2, and so forth. So what we're first going to do is think about how many total levels we expect the skip list to have. So if I add n items to a skip list, the number of levels it's going to have really depends on what's the biggest outlier in my coin flipping process. Turning that around, conversely, it's at what level do I expect to have only one element on average, right? So if I take n and I divide it by a half, k times to get a level with one element, I know this math is going to be really familiar. I have 1/2 to the k is equal to 1 over n. I will invert both sides, and that will get me 2 to the k is equal to n. I think we all know where this is going. We'll take the log base 2 of both sides, and we get k is equal to the log base 2 of n. This just keeps coming up. Now, we could say, well, we could make this number of levels smaller by using a third instead of a half, or a fourth, or a fifth. And what we saw in our discussion last week about the big O idea is that when you think about the order of growth, those constants don't really matter very much. So the same idea would work if we made the probability a third or a fourth or whatever. But there's a trade-off here, right? If you insist on having fewer levels, then at each level you're going to have to do a little more searching to find the value you're looking for. So in general, we're actually better off, I think, with more levels. And so 1/2 is the probability that we stick with for this purpose. So this is the expected number of levels that we're going to have in our skip list. So next we have to think about, well, that's still not telling us the number of comparisons by itself, right? We still actually have to figure out how many total comparisons are happening given that we know how tall the list is. So let's just look at our example to get some idea of what this might look like, and then we're going to turn this into a more general idea. Let's assume at the top level, you're going to do one comparison. At the next level, you'll do 2 comparisons. At the next level, you'll do 4 comparisons, and so forth. So what this suggests is a summation. I equals 0 to log 2n of I. Well, this isn't quite right. 2i. Okay, it's still not right. We want to start I at 1. No, this is still not right. It's 2 to the I. There we go. So this is equal to 1 plus 2 plus 4 plus 8 plus 16 all the way up to log 2n. Now, as it happens, once this particular sequence converges, I'm going to skip the details of this for now. It's going to be very close to this. Let's see. It's basically going to be 2 times the log base 2 of n. So given that, we say that the expected case for this, for a search of a skip list is big O of log n. So again, this is the number of comparisons we expect at a given level. Top level, we have just 1. Next level, we have 2, and so forth. This can be wrong, obviously, especially if we get unlucky with which nodes happen to be the tall nodes and so forth. But in general, with a sufficiently large list, this is going to work out pretty well. Let's think about, so that's just lookup. Let's think about adding. To perform an add, how many additional comparisons do I need after the lookup, if any? When I was adding, inserting, did I need to do any additional comparisons after my lookup?
I don't think so.
Yeah, maybe 1 tops, right? So in other words, if a lookup is at O of log n, adding doesn't really differ from it by a constant, by more than a constant. So it turns out this same analysis applies for an add. Now, coming back and examining it again, we can think about the equally interesting problem of a remove. I didn't do any removes in my earlier example. Let's do a couple now and see how it works. the first thing I'm going to remove is 3. So I come here, I do my lookup. 3 is less than 5, I go down a level. 3 is greater than 2, it's less than 5, I go down a level. Look, there's 3. So I'm going to take the pointer at 2 and have it reference the node after the 3. And at that point, the 3 is no longer present in my skip list. How much extra work was that? It was a constant, right? So far, remove is looking pretty good. But let's do a remove that's maybe a little more violent.
Maybe like 2 levels high.
We're going to remove 5.
Oh.
So we look at our top level, and we find 5 pretty quickly, right? So we need to remove the entire node. So that removal process means at every level, we're going to bypass it. So at the top level, we are now null. So that effectively eliminates it there. At the next level, we are now pointing at the 6 node. And at the bottom level, we again do the same. So it's still no more than log n work, right? I had to do a removal at every level. So it turns out remove is also just big O of log n. So this is a pretty powerful idea. My skip list is kind of robust to the pressure. If we look back at it. Now, we're still kind of counting on being lucky. In a way, the skip list is revenge of quicksort. Each list, if you imagine quicksort with a randomized pivot, each list is really just randomly selecting a pivot value, so to speak, that lets you rule out half of the level below in some form. So all of these ideas just keep popping up in different forms, in different ways, as we think about this overall problem of sorting and searching. Any questions about the skip list? Now's a great time to ask because, 28 hours from now, you're going to be implementing one. Yeah, Elijah.
What practical uses?
What's the practical? Yeah.
I mean, I get the practical use, but like, what outside space is it used? Like in a, I guess, workplace.
Sure. A skip list is a really nice way to implement a dictionary, like we see in Python. Now, in fact, a lot of what we're going to be looking at from here on out are effectively different ways to implement dictionaries, which have different trade-offs involved with them. So a skip list is a very effective technique for implementing a dictionary, such that because lookup, add, and remove are all just log-based 2n comparisons, you can insert something in a dictionary, the key value pair. So typically in a dictionary, the key is what we're sorting on, right? and then there's some value associated with it. So this would give you log n, lookup, add, and remove from a dictionary. It has the additional benefit that your dictionary is also perfectly sorted. So if you want to output the values of the dictionary in order, you get that in linear time effectively because you just walk through the list. Getting it there, of course, takes n log n time. And this is an important insight, right? I mentioned that n log n is the best you can do for sorting. Notice that if you insert n items into a skip list, each insert taking log n time, we still have n log n. We haven't beaten that little curse, right? So that can be a really helpful property because dictionaries wind up being a foundational data structure for other more complicated or involved data structures as a practical matter. And so in particular, if you want to examine it as a string, having it already in sorted order is really valuable. Another way of thinking about this issue is if you want to see if two objects that are both implemented with a dictionary have the same stuff in them. If they're in sorted order, it's really easy to just walk through them and check to see if each corresponding element is the same. And so that's a really powerful idea. A very, very powerful idea. The skip list also has some other useful properties that some other data structures we're going to look at don't really have, which is it's pretty easy to imagine creating a skip list that exists across multiple machines connected on a network. So if you have an extremely large data set, like several billion items, say, and this kind of stuff comes up in practice, you can imagine partitioning the items using the skip list idea. So that you've got some nodes that say, well, I'm not actually pointing somewhere in memory. If you're going to skip past here, time to head to the next computer in the network. And so it can actually be a way to create a distributed collection that exists across multiple machines. The skip list idea, in turn, lets you then bypass entire machines as you're looking for something and save on the expense and overhead of the network communication. And that, too, is a pretty powerful aspect of a skip list that really doesn't exist for any other data structure for doing this. And I'd say that's a very unique niche for the skip list in particular. Aficionados of guaranteed log n, insert, add, remove might poo-poo the skip list a bit. And in fact, that'll give us something to do next week when we start looking at what's called a binary search tree. But the skip list is kind of uniquely interesting in that regard as well. It's a really powerful data structure. And as long as we're lucky, and with large numbers, we will be, in fact, lucky. This is kind of a golden optimum for sorting and searching. We're going to find another technique for sorting and searching that in practice does better than this. That's still a few weeks away. But in theory, it's hard to do better than these log in, insert, remove, lookup. Cool. Any other questions? Happy skipping. I will see you all in lab tomorrow.